Thank you for doing that, and I'm sorry for this little hiccup. So it's a pleasure to be here and to share the latest news really on neutrino physics. This is an experimental talk, so I'm mainly focusing on the experimental results. Page 2. So this is the outline of this talk. So what I'm going to do is to first give an overview about what we know about neutrinos at the moment, so what's the current landscape. Then I will focus on long baseline neutrino experiments, so the current ones, T2K and NOVA, and then DUNE and Kamiokande. Then now we are in 2020, so they're not anymore the next decade, but they are in the current decade. Then I will discuss the neutrinos using reactor experiments, so where we stand now. Then how can we measure the neutrino mass? So these latest topics will be really just a few highlights on what the recent results are. And then really I will just highlight some further topics to be investigated really in the future, but they are not the topic of this talk. So really the focus is long baseline neutrino experiments. Moving on page 3. So this is what we are actually doing now, and then page 4, yes, so neutrino oscillation framework. So we know what neutrinos are, but just to remind you that they oscillate. So there is a mixing matrix that relates the flavor and mass eigenstates, and this is called PMNS. This is a 3x3 matrix, so you may be familiar with the CKM matrix, and this is again a unitarity matrix, but these the parameters are very different. So since this is a unitary matrix, so we do have again just 3 real parameters that are 3 rotation angles and 1 complex phase. The convention is that they are called theta 1, 2, 2, 3, and 1, 3 for the 3 real parameters, and delta CP, so the CP violating parameters for the phase. These matrices can be represented as the product of 3 rotational matrices, and the parameters basically are related to different kinds of neutrinos, sector really, so depending on their characteristics of energies and the distance from the detection. So these are the solar neutrinos, accelerator reactor neutrinos, and atmospheric neutrinos. If you look at the formula, then there are the neutrino oscillations. This is for the particular case of 2 neutrinos, so just the oscillations between the flavor A and B, and this depends on the parameters that depend on the neutrinos that are theta and the difference of mass squares, but then parameters that depend really on the experiment you are performing that are L and D. And if you are natural experiments, you don't have so much choice. You can change you can't change the parameter, the energy, so distance from the sun, but you can do something if you do have something on Earth, human-made. But the other part I like to highlight is that delta M square needs to be, the sign of delta M square needs to be addressed using matter interactions. So it doesn't work if you just use a vacuum equation, so like this is the one you can see in front of your screen. So at the moment, just delta M square 1, 2 has the sign defined thanks to neutrinos going through Earth, but not delta M square to 3. And so there are 2 different scenarios. So you can have a so-called normal ordering and inverted ordering. So you will see these 2 categories a few times in the future slides. So moving on to the next slide, this is the formula of neutrino oscillations for the case of 3 flavors. In particular, you can see that there are different terms that appear. So the CP conserving term, but especially CP violating term. So we can measure CP violation, and as well, you may have a term that depends on the matter, the interaction of neutrinos with matter. You can look at two different configurations, really, once you have a beam of neutrinos. You can look at disappearance of those neutrinos, in particular here, the muon neutrinos disappearing on the left-hand side, and on the right-hand side, the electron neutrinos appearing from a muon neutrino beam. So you can look at two different cases, and especially you can see the maximum of depletion. You can position your beam in such a way to have the energy needed for maximize the probability of oscillation. If you move on to the next slide, then you can see what the current status is from phenomenology phase from the NUFIT collaboration. This is based on the available results at the time at the end of 2019, and there are a few main pending issues. So the mass ordering, that is the brown arrows, so with the no for delta m squared to 3 design. We don't know the value of theta to 3 exactly at the level to know what the octant is, which changes basically the composition of the corresponding neutrinos, and the CP phase, which is still something that we are trying to address. If you move on to the next slide, so the open questions in neutrino physics are many, and the main at the moment is really the determination of CP violation, so that can be achieved with long baseline neutrino experiments. Then what are the precision? What is the precision of the mixing angles? I mean, do we know them enough? What, for instance, theta to 3 is? Then what are the values of the maxes? So we can either look at the difference in masses, so the sign, the ordering, or we can look really at the absolute, so at the direct mass measurement. And then what the nature of neutrinos is, so whether they are Dirac or Majorana. And of course, we can look at astrophysical neutrinos, etc., non-standard models. These are not addressed in this talk, actually. So there is generally a very, very exciting program in neutrino physics, and I think it looks more exciting even for the future. So move on to the next slide. So now I will have the majority of this talk that is going to focus on long baseline neutrino experiments. So let me start with T2K in the next slide. So the neutrino experiments, here you can see a plot really of the cross-section as a function of the neutrino energy. We do have several neutrino long baseline neutrino experiments, and they do span different energy ranges. There are different cross-sections associated to that, and the cross-section is a major item for study really for the current collaborations. And you can see that the macroboon and T2K, upper K have a lower energies, higher energy for nova, DUNE of the order of GVs really, and then we move on to astrophysical neutrinos like PINGO, etc. Right, yeah, we can move on to the next slide. So the T2K experiment, this experiment is based in Japan, as you can see this diagram. The accelerator is just north of Tokyo at Tokai, and the accelerator complex that is in the aerial picture on top that has provides a neutrino beam that runs from J Park to the other side of Japan. This goes 295 kilometers away to Super Kamiokande, that is a 50 kiloton water Cherenkov detector. The characteristics of this beam is also that it is tilted, so it is an off-axis beam, 2.5 degrees of axis. Why is it that? Because of the pion kinematics, the neutrinos coming from the interaction basically of the protons with the target. The target you have the pions, and then from the pion decays you have the neutrinos. So because of the pion kinematics, then you do have a narrowed beam if you do use a tilted angle, an off-axis angle. So what we are looking at are a beam produced at J-Park, which is a snapshot, if you want, is taken at the near detectors, and then at the far detector you compare what you observe at the far detector, that is oscillated neutrinos, with what you assume you had at the near detector, so when the beam was generated. This is a general principle for long-based neutrino experiments. So I will always talk about near and far detectors. In this specific case, they are near detector, that is a tracker detector, and the far detector, this is with the chunk of detector. And what we want to see is oscillations. You want to see neutrino oscillations that either they have a disappearance, an appearance of electron neutrinos, for instance, in this case, or anti-electron neutrinos, but you may look as well as a difference between electron and anti-electron neutrinos. Page 11. So this is just the protons on target. So basically, if you are in a collider physics, this is the corresponding of the luminosity, integrated luminosity you're looking at. And we are looking at basically a 50-50 sample of neutrinos and antineutrinos. And almost all the ones that have been collected by T2K have been analyzed for the next results I'm going to show. So on page 12. So what's the principle then? So you, as I mentioned, what you want to give is basically a snapshot of what you have at the near detector before you can compare that with the final, with what you observe in the far detector. How do you do that? You need to know exactly your beam, actually, the beam that is generated from the interaction of the protons with the target. But the hydro production is not so well known. So there is a dedicated experiment in the case of HyperK, and also DUNE will use, for instance, shine, etc. That is an experiment at CERN that, as far as the neutrino experiments are concerned, provides the information for narrowing down the hydro production. But at the same time, you do have information from the interaction with the from the measurements at your own beam, your own target. So then you do measure the neutrinos at the detector, at the near detector, and you do have several configurations in neutrino and antineutrino modes. You're looking at charged current interactions. So you do have a W, you have a charged muon, positive or negative, and you may or may not have, depending on the final state, you're looking at pions in the final state. So you are looking at several samples, 14 in the case of the near detector for T2K. And then you are basically combining all this information together with the interaction model you have in order to extract the information that you want to compare with what you see in the far detector, that is a super Kamiokande, where you do have different samples. Again, you're looking at the charged current interactions of the neutrinos with the nucleus, so in this case with the chunk of detectors, so water. And yeah, you have a similar categories in which you will look, though, for the specific case we are looking at is the appearance of electron neutrinos for the appearance CP violation, or the disappearance of mu neutrinos for the disappearance. Moving on to the next slide. So this is the samples for the disappearance. So you started with the generic neutrino-muon beam or antineutrino-muon beam. You look at the results at the superchemical detector, and you can see there is a disappearance in the top plot of neutrinos. So you don't have the solid line that you would have observed, but you do have a depletion. And similarly for the antineutrinos. So if you do a fit, you are able to find contour levels in the plane delta m squared 32 sin squared 32, and you can see these results, especially in the top plot, where there are also other experiments, other results, and the blue is T2K, where the corresponding value of sin squared theta to 3 is still at the edge really of the octant, so we are not able to distinguish between the two octants yet, as well as so it's consistent with maximum mixing, but there is more information regarding still that m squared 32. So let's move on to page 14. So what about the appearance samples? So in this case, you do have you are the technique, the fire detector, really, the electron-neutrinos. So you see what you get from the oscillations, and these two plots indicate the reconstructed energy for neutrinos and antineutrinos, electron and antineutrinos. What's table here indicates the number of events you observe and the corresponding systematics. What I like to highlight of the systematics is that the very important systematics are related to the flux, as we mentioned, that we try to address also using external detectors, and the cross-section, the interaction of the neutrinos really with the nucleus. These are really crucial systematics that.
Sorry, I lost your sound. Sorry, any sound?
Can you hear me?
Yeah, now it's okay.
Okay, thank you. Next slide, please. So here you can see the electron-neutrinos versus antineutrinos. Where the indication really is that you have more electron-neutrinos and less anti-neutrinos than expected really. So you do have an indication really of CP violation. If in this plot you can see actually the data from T2K as well, what would be the really the areas, the curves for different values, the parameters of sin squared theta to 3 over CP violation. So in this case, a negative value of delta CP is favored over a positive value. Normal mass ordering is favored over inverted mass ordering, and there is a weak preference for the upper octant, but there is no indication of that yet. So this is what we can observe for this measurement. If you move on to the next slide, please. So more on the CP violating phase. So I just highlight what the main results here are, is that you can for the first time set up 3 sigma intervals for delta CP. You can exclude 2 sigma, the CP conservating cases, it actually a 3 sigma except for one case that is a normal ordering at 180 degrees. So there is quite a lot of improvement of knowledge that now we are bringing forward, and we hope with more statistics there will be the possibility to improve more this information. There is as well the results are using reactor, not reactor neutrinos for the value of theta 1,3. Moving on to the next slide. These results are on Nature. These are really recent, although you can find the corresponding paper really on the preprint server. And the T2K results, as you can see, exclude most of the region for delta CP, assuming most of the region of delta CP. So these are really moving forward to have a 3 sigma observation fully of delta CP. Let's move on to the next slide. So so you may wonder what's going to happen. So in the next decade, which is actually the current decade now, the plan is to increase the beam power since the next experiment that is Happy Kamiokande has been approved. So the beam has been approved to reach the 1.3 megawatts for Happy Kamiokande. So there will be a constant upgrade of the beam. This is in parallel as well with an upgrade of the NEA detector, as I mentioned, is crucial for the determination of the cross sections. And this is up to 2025, up to when Happy Kamiokande will be at the verge of being starting to take data. One thing to highlight before we move on to the next slide, the Super Kamiokande has been doped with gadolinium, or will be doped with gadolinium, has been refurbished. Actually, there is a slightly delay due to the COVID-19. Let's move on to slide 19. This brings me to the experiments really in the US. So there is a strong accelerator program at FERMILAB with actually several beam lines. What I'm interested in at the moment is really the one for NOVA and then LBNF, so DUNE. But you can see as well NOVA, like T2K, is also an off-axis beam, differently from DUNE. And DUNE in particular also addresses both the first and second maximum, oscillation maximum. Let's move on to the next slide. This is just a snapshot of NOVA, where the two detectors, near and far detectors, that are one at FERMILAB, the other one at Ash River, and those are very different in size, but they are technically the same detector with liquid scintillator. So you really are able to have the same systematics between the near and the far detector. There is a long baseline between the FERMILAB at Ash River, so we are talking about 800 kilometers, so this is much different from Super Kamiokande, and in this case then you are able to address the mass hierarchy, so you will be able to measure delta M square. The detector has been running, the experiment has been running since a few years at 700 kilowatts, so fairly high, and the number of neutrinos and antineutrinos is going to be similar. So these are functionally identical detector, but they are very difficult to, especially the fire detector is very challenging because it's a detector on the surface. So you need to have a system to remove really all the background that comes from the atmospherics. And there is a complex system with a neural network, a convolutional neural network, to get rid of those events. If you go on page 21, then I'll just show very quickly the results, which are the same as in the sum. So NOVA as well is able to address the disappearance and appearance of electron neutrinos and disappearance of mu neutrinos. Here are the best fit results with the corresponding value on the upper right plot, really, in the by probability plot of S square theta 2, 3. The inverted hierarchy is disfavored 1.9 sigma, and delta CP greater than equal the conserving value equal pi half is ruled out at 4 sigma. All the values of delta CP are allowed at 1.1 sigma. Moving on to the next slide.
Francesca,
yeah.
We have 5 minutes left, just to remind you.
Yeah, so so you can see the current results for delta CP as well as the comparison between the different detectors with different experiments. Let's move on to the next slide. NOVA also is planned to take data for a long time, and there will be improvements to the detector, and these are going to be in the direction to improve the systematic errors, as you can see. So there is still a large statistical uncertainty, but you want to decrease as much as possible the systematic uncertainty, especially with new test beams. The next slide, I move on then to the experiment, just to highlight this is very briefly because they will require quite a lot of description. So the neutrino-nucleon interactions, as I mentioned, there are major systematics. You may look at the neutrino interactions with the nucleon as well as the nucleus level. And the current measurements are statistically limited, not for long, but especially it's essential to decrease the systematic errors for the future experiments, DUNE and K. Next slide. You can see there are different neutrino interactions, and depending on the different experiments on the right-hand side, they are sensitive to different neutrino energies, so to different neutrino interactions. But what is important that I wanted to highlight really is that there is ongoing a global program of measurements of different types of interactions, different materials. And this is really important because in order to understand the models, the interactions, you need to have to try to over-constrain the different cross-sections using different targets and experiments. Next slide. This just shows you that none of the current simulations really are able to describe more than the electrokinematics, but there are many measurements, and there is really a campaign also with an ER detector that is ongoing to try to address these uncertainties. Then in the next slide, we move on then to DUNE, which is the flagship experiment really in the US. There have been recently 4 volumes really with the description of the experiment, the physics. So the experiment is very advanced, and I will show some results. But you can see that there is a long beamline of 1,300 kilometers from where the beam is produced at FERMILAB with the fire detector in South Dakota, where the fire detector is 4 modules. There are 4 times 10 kiloton fiducia volume each, and at least the first one will be a single phase liquid argon TPC. The NER detector as well is very complex. It's a set of tracking system, but it has also the argon that is the nucleus that you adopt, to which you have the interaction to in order to extract the systematic errors. Next slide. So I just quickly show how well the situation is for PROTODUNE, the single phase. PROTODUNE is just a small size really of as you can see here in this diagram, of what will be actually the fire detector. And here you can see one plane, and this has been actually built at CERN. So in the next slide, you can see that this is what was before at CERN, and then what happened now with the 2 double and single phase PROTODUNEs. And I will just describe it in the next slide, the results about the current performance of the single phase, which has been progressing very well. So the LAR purity is very good, as well as the noise signal to noise ratio, calibration is ongoing. D of the X is quite nice to see that, as well as the identification of the protons. But there are several measurements that are underway, and it would be nice to see very soon, actually, the cross-sections, measure cross-sections coming from the interaction of the charged beam at CERN with the detector, with the liquid argon. Now,
Just sorry to interrupt you again. You have like 30 seconds left, so please come to an end.
yeah. Okay. So I will just at this point I will just show I guess
conclusion.
Yeah, the conclusion, I guess, at this point.
Let's start. Is this
Yeah.
funnel? This is funnel.
Yeah, okay. I can just show here. So
Oh,
yeah.
sorry. Which slide go to?
So there are so page 55 actually.
50.
Yeah, so what I mean, the main highlight was the results really from T2K, so with the CP violation. The other results were indicating there is an intense program worldwide to understand the neutrino properties, to understand again, CP violation and the mixing matrices, as well as parameters of the mixing matrix can be determined as well as delta m squared, the reactor neutrinos. DUNE in particular is able to address the delta m square, as well as direct mass searches. There are recent results from Catherine. Still, we need more data and addressing the systematic errors. And then the nature of neutrinos as well is a major open question. So there are also neutrinos that will better the case to address the Dirac versus Majorana types of neutrinos. And we are looking forward more results in the next days and next years. That's all.
Thank you very much, Francesca. We already have a question from Carlos Wagner. He's asking, the determination of the CP violating angle at T2K seems to be held by some tension with the standard model predictions, meaning that the effects are larger than expected for any CP violating angle. Also, there's some tension between the NOVA and T2K results. Could you comment on these facts?
Yeah, so for the first one, I think we will need to see with more statistics. So the experiment is supposed to continue to take data. We'll have an improved near detector. So I think we can see in the future what's going to happen. As far as the so-called tension with NOVA, there is actually an ongoing working group that aims to provide that is going to provide combined results from the two experiments, so we will see what happens. We still need to see future updates from NOVA. So we will see then what they hint to. But the two collaborations are working together, which is good. I think it's premature to say there is something yet there, but yes, I do agree that there are some differences.